Good evening. So today we'll be looking at F distribution as a type of continuous probability distribution. Sometimes now we have been discussing probability distribution, and we talk about discrete, the different type, the probability distribution are divided into two different types: discrete and continuous probability distribution. Under each category, we have unlimited number type of distribution. You can only talk about the commonest ones we encounter in in solving everyday. So you see many people discovering new distribution, but each of those distributions will either be a type of discrete probability distribution or a continuous probability distribution. So we have been talking about, after discussing discrete probability distribution, we started discussing continuous probability distribution, and there we have discussed normal distribution, then followed by chi-square distribution. Then the last one we discussed was T distribution. Today, which will be the last continuous probability distribution we want to discuss, is F distribution. The F distribution is also known as Fisher-Snedeker distribution. It's named after those two geniuses that describe the distribution. This is a picture of Sir Ronald Fisher. A continuous probability distribution is the distribution of all possible value of the F statistic. So to understand what F statistic means, is the ratio of two variances. So it's actually comparing two variances. That is, if you have two population or two samples, you can calculate the statistic, which can be anything, maybe mean. Then the variances, the spread around the measure of central tendency variances is the variance or measure of variability. So when you are trying to compare the variances in two samples, that is F. So it's achieved by division. You compare the variance not by removing one from one, you divide one by the other. So what you get is F statistic. So the distribution of this F statistic, F distribution, it was developed by Ronald Fisher and George Snedeker to study the behavior of two variances from random samples taken from two independent normal population. Of course, when we say normal population, F distribution, the assumption is one of the parametric tests. F test, one of the parametric tests. So there's an assumption that the underlying characteristic or variable follow a theoretical distribution. Let me use this notation. So in applied problem, we may be interested in knowing whether the population variances are equal or not based on the responses of random samples. So you want to compare two variances, like when you talk about homogeneity of variance. If you have two variances, you want to see, are they the same? That's homogeneity of variance, is F. When you are running t-test and you see with express you run t-test, it first of all give you something like homogeneity of variance, 11 tests, see something like 11 tests. You try to divide two variances. That is a form of comparing variances. Is F. The statistic there is F. As you're going to see, the F statistic is not only used for that purpose, though the other purpose is you can actually see that it's in us the situation is comparing two variances, but in some cases you just compare two variances to see are they homogeneous. In some cases it's a form of statistic that test a non-hypothesis like the ANOVA. We're going to look at it quickly. But let's first of all look at the characteristic of this distribution, the shape, and we'll look at some pictures, the graph to actually conceptualize, to be able to have a mental picture of how it looks like. The curve is not symmetrical, but skewed to the right. So you remember that in standard normal distribution, it's not skewed, it's bilaterally symmetrical. We remember that T distribution is not skewed, bilaterally symmetrical, but the peak and the flatness, the base and the peak is what differ from that of normal distribution. As the degree of freedom increases, the T distribution approximates normal distribution. So the T distribution is primarily like its best shape also, bilateral symmetrical, but it's quite different from standard normal distribution. And once the degree of freedom increases, it approaches normal distribution. Chi-square distribution is skewed to the right. As the degree of freedom increases, it approximates normal distribution. The same thing, the F distribution is skewed also. You're going to see actually the origin. You know, we talk about the origin of chi-square is when you square Z, which is standard normal deviation, it gives you chi-square. If you divide 2 chi-square, it gives you F. Those are the origin. If you divide, you're comparing 2 chi-square, it gives you F. So the F distribution also is skewed to the right, just like normal, just like chi-square distribution. There's a different curve for each set of degree of freedom. So like chi-square distribution, like T distribution, F distribution depend on the degree of freedom. So it's a family distribution. So different degree of freedom, different shape, different graph. Unlike standard normal distribution, there is only one. So the chi-square distribution is a family distribution that depends on the degree of freedom. The T distribution is a family distribution that depends on the degree of freedom. The F distribution is a family distribution that depends on the degree of freedom. Can you see all of them? All those chi-square, T, F, as the sample size increases, as the degree of freedom increases, they approximate, they look like normal distribution. We're going to see something that make F distribution different from chi-square and T distribution. Okay, just like before that, just like chi-square also, the F statistic is greater than or equal to 0. So T, it doesn't have negative side. You know, unlike normal distribution that is negative, that is positive. T distribution that is positive, that is negative. But actually, they can be less than 0, greater than 0. But chi-square has no negative. You know, it was gotten by squaring Z. If you square anything that has negative, when you square -3 times -3 will give you plus. So the chi-square is from 0 to just upward. It's less than or equal to 0. The same thing with F distribution. Now, the only difference now, once the difference, the unique difference that make F distribution differ, or the unique characteristic that make F distribution differ from this chi-square and T is that the degree of freedom for the numerator and for the denominator, okay, there are 2 degrees of freedom. That's just it. There are 2 degrees of freedom for each distribution. Unlike chi-square is 1 degree of freedom, but here there are 2 for each graph. There are 2 degrees of freedom because it is a ratio. We say that we're comparing 2 variances. You divide variance 1 by variance 2. So we have one that is numerator, one that is denominator. So each of them has its own degree of freedom. So the numerator has its own degree of freedom. The denominator has its own degree of freedom. That's what makes it unique. So as the degree of freedom of the numerator and denominator get larger, also it makes the distribution to approximate normal distribution. Look at the different graph, just showing, explaining what I've just said now. You will see there are 2 sets of degree of freedom for each graph. This red graph now, the numerator is 1, the denominator is 1. D1 is numerator for the denominator, degree of freedom for the denominator. For this one, can you see? For this other one, dark one, 2 and 1. For this other one, blue, the numerator is 5, denominator is 2. For green, the numerator is 10, denominator is 1. For this ash one, the numerator is 100, denominator is 100. You can see it looks like normal distribution. If you see all those other ones, they are skewed to the right. But this last one is look like normal distribution because the degree of freedom has increased. The degrees of freedom are very large. So the graph has approximated normal distribution. So still look at this second graph also. You see, look at the last one, which is this orange color. The degree of freedom are 13 and 50. They are big enough. Whereas the other one with smaller degree of freedom, you can see their skewness. They are not bilaterally symmetrical. They don't look like normal distribution. But this one now, the last one, this orange color graph, look approximate normal distribution because the degree of freedom are large. So if you look at the last, the third one also, the same. You see some of them that look at this one. Infinity means that when you see infinity, it means that it's the second degree of freedom, which is denominator, that is very large. When something is infinity, it's very large, approximately big. But if you look at the numerators when they are small, and the other one is infinity, it will still be skewed until both of them, both numerator and denominator degree of freedom increase. It will not look like normal distribution. Look at this one now. The summa for all those graphs, the numerator and denominator are somehow large. That's why almost all of them look like normal distribution. That's the picture. You can see what differentiates the F distribution from other continuous probability distributions, that it depends on 2 degrees of freedom. Now, application. In what situation do you apply F distribution? Is if you have a question, because you will soon stop, type your question so that you can attend to your question. You can type your question and chat it. The F distribution is used in many cases for critical region, for hypothesis tests and determinist confidence interval. The 2 common examples are ANOVA, analysis of variance. When you are comparing quantitative variable or mean, you are comparing mean of more than 2 groups, maybe 3 groups, 4 groups, 5 groups. So there is no point doing t-tests because t-tests only compare 2 mean at the same time. But when you have 3 mean, if you have to compare 2, 2, 2, you have to pair them in many ways. If there are 3 mean, you have to pair 3 mean in 3 ways. So that you carry out 3 t-tests. If there are 4 groups, you have to carry out 6 t-tests. If there are 5 groups, you have to carry out 10 t-tests. Can you see? You know, you are, apart from the fact that it's cumbersome, carrying out too many t-tests on the same data set, there is this risk of family-wise error. You are likely to have at least one to be significant. When normally there's nothing should be significant. If nothing should be significant, you find something significant. It's just like somebody that doesn't know anything, it's $1. If you keep on writing an exam over and over, one day will pass. It doesn't mean that he knows it. The person just pass. So making an attempt over and over, he can break through. Doesn't mean that he actually know what he's doing. The mere attempting is the same thing. So when you carry out too many tests. So in ANOVA, what ANOVA now does is to, rather than comparing the mean, compare the variances. Call it analysis. It's just a unique statistical method. And the statistic we use there is the ANOVA, is the F statistic. It follows F distribution in the sense that it's the analysis of variance. So F statistic is comparison, is division of 2 variances. So that shows that when you analyze one variance, so from there you even know, we have already said that F statistic or F distribution has 2 degrees of freedom, one for numerator, one for denominator. So we have 2 variances, one is denominator, one is numerator. So analysis of variance is that you analyze the numerator variance and the denominator variance. to compare them. So that is why F statistic is a statistical choice. And the funniest thing is that that ANOVA, as you are going to see also, is what you see in regression. Actually, ANOVA and regression is the same. They are two faces of the same coin. So that is why when you run regression, you see ANOVA there. So we are going to look at them, how their degree of freedom, at least how they are related. We look at them also. So F test, just to determine if the variances of the two populations are equal. Actually, all of them are F tests. Even the ANOVA is a form of F test, but since it has its own special name for a particular purpose, analysis of variance. So the homogeneity of variance is F test. Then you did Levene test is F test. So anywhere you are comparing two variances, you are getting F statistic. This is a form of F, but we call those one F test, call this one ANOVA. Even the ANOVA, when you just do ANOVA on its own and when you do regression, it's different, but it's the same ANOVA. So here now, I could have just said, okay, examples are ANOVA, regression, F test. All of them are the same thing. It's just different way. Different way, just like the way you have doctor. So some of you are surgeon, this one is internal medicine, this one is urology, this one is a pediatrician, this one is a cardiologist. All of you are consultant. Then you are manifesting in different way. It's the same thing, the F, either in ANOVA or F test or in regression, doing the same thing. So let's look at the logic. Now, so I just call it the degree of freedom for, but let's just look at the logic, because we've said why I put this one here. We have earlier said that even the shape of the distribution depend on the degree of freedom. That is, we have different. It's a family distribution, so we have different type of the distribution, different shape, depending on the degree of freedom. So how do you conceptualize the degree of freedom? And we already said that since the degree of freedom, there are two degrees of freedom. So how do you conceptualize it? And that's what I want to show here. We want to look at it for ANOVA. When you look at it for regression. Even those regression also is in form of ANOVA on its own. But it's quite slightly different. Now, EF is a statistic for ANOVA, as I've said. And what F does is, okay, variance over variance. Variance, another name for variance is mean square. If you remember, some of us that watch our video on descriptive statistics, where we talk about mean, standard deviation, how do we generate standard variance and standard deviation from the mean. And also the last set of lecture we were given when I talk about understanding statistics beyond the basic concepts. I revisited those issues on all those rudimentary aspects. We talk about mean, then when you remove the mean from each value, that is x, each value is x, mean is by x. You remove it, it gives you deviation. That deviation from the mean. And we said that if you add all the deviation to be 0, so we don't have the intelligent people know, okay, let's square it. When you square the deviation, and now, okay, you now add everything together. That will be sum of square deviation. SS, sum of square deviation. But that sum of square deviation is just like you just add everything, but you want to calculate the average. If you want to calculate the average of the sum of square, you divide by the degree of freedom, which is n-1. It gives you the variance. So if you look at it, it's the mean average of the sum of square deviation from the mean. Is the average. So the average is not gotten by divided by n, but by divided by n-1. So variance is the mean deviation from the mean, or average deviation from the mean. So it's the mean square. You know, we have a sum of square, the mean of it. So sometimes you see mean square, it means the same thing as variance. Mean square, variance. So between groups, so variance or mean square between group. You know, when you are, let's say you have 3 groups now, you want to analyze the variance. The 3 groups, there are differences in the value of the 3 groups. So the variation, the variability you observe among the three groups is the mean square or variance between the group, And that is what serves as the denominator. That variance is what serves as denominator in F. In numerator rather, please. Numerator in F. That's sum of variance, mean square between group. But we know that inside each of the group, there are variability in the value. The value are not the same. So the variance within the group is the variance within, which is mean square within group. So what ANOVA does, or F ANOVA, is to divide the variance between the groups, three group, and the variance within the three group. So variance between divided by variance within. That is the F. So another way of saying mean square, MS, between, that's why I could put B, between divided by MS, which is mean square within. So it's seen as a model where I differentiate that in the word, okay, when you say model, okay, because this one can, I think, let me quickly, there's a slide, the last one, let me quickly go there because for you to understand when you use the word model. Now, the same element as you have seen it between group, within group in ANOVA. When you get to regression, which is the form of ANOVA also in the regression, where you don't call it between group because the group is not, you are not talking of group. The way you arrange, you organize the regression is different from the way you organize, okay, ANOVA in groups. So what we call numerator, which is between group, in regression, it is called model, because that is a regression model. So what is between group in ANOVA is the same thing as model in regression. So what you now call within group in ANOVA is what we call residual in regression. So we'll not talk much about that because we have talked extensively. We have done regression. So if anybody can go and watch the video, we will iron out the model and residual. We are not going to that now. I just want to differentiate the terminology. It's the same thing in ANOVA, in regression. So what you call between group variance in ANOVA is what called model in regression. Within group in ANOVA is called residual. Now, look at it. So when I call it model, I'm just missing word here. That is sum of square between group over sum of square within group. I'm just repeating it, which is F. Now, there are two degrees of freedom. That's where we are going. One for the numerator, sum of square between group. What is the degree of that sum of square? The variance between group, the degree of freedom. So the degree of freedom, we have already talked, if you remember, when we talk about degrees of freedom, is entity minus one. Entity minus one. So if we have three groups now, we want to compare. The degree of freedom for the numerator, which is between group, will be the 3 minus 1. So J here means the number of the group minus 1. So the number of group minus 1, J minus 1. So the degree of freedom, that's the first one you see, the degree of freedom between, for the numerator is the degree of freedom between group, which is all the degree of freedom model in regression is number of the group minus 1, is J minus 1. Then the second degree of freedom, which is for the denominator, the number of the denominator, the one for the denominator, that's mean square within. The sum of the degree of freedom for the group. No, we have, let's say we have 3 groups now. For each group, they have their own, the number of degree of freedom for each group, because each group contains certain, there is sample size for each group, maybe 10, 10, 10. So for that 10 now, if it's 10, 10, 10, for the first group, it will be 10 minus 1, which is 9. Second will be 10, the number of the minus 1, which is 9. For the third one will be the number minus 1. Sometimes it may not be the same. The group may not be. So if it is 10, 12, 15, it will be the sample size minus 1 for each of them. You now sum the degree of freedom for all the three together. That is why it is sigma. Can you see? Sum of n minus 1, that is the n minus 1 into the number of group we have. Now sum everything together, which is the degree of freedom within group, which is for the denominator, which correspond with the degree of freedom residual for regression. Because for the regression, the denominator we are talking of here is the residual, while the numerator is the model. But here in the ANOVA, we call it the numerator as the between group and denominator as within group. So the total degree of freedom will now be the sum of the degree of freedom for the numerator and denominator to give you the total degree of freedom. Now let's look at the way it works for regression also, since we have made mention of that regression. Now, in regression model, each term is estimated parameter that use 1 degree of freedom. For example, now for simple regression, what we mean by simple regression is that the outcome variable is 1. All the regression anyway, the outcome variable is only 1 variable. But the exposure variable may be many, maybe 1. So for simple regression, apart from the fact that the outcome variable is 1, the exposure variable is 1, only 1 also. In that case, like this x1, only 1. This b0 is constant. So when you are talking of the estimated parameter here, we have 1, 2, there are 2 here. For simple regression, there are 2 parameters there in this equation. Apart from the y, this is b0 and b1. This is regression. Okay, we are not talking about regression, so I will not go into that detail. I just know this one is just the error, which we are calling residual. That's what they call residual. Is the error, which is the residual. Now, this b0 plus b1 s1 is the model, form the model. This is the error. Model plus error. Can you see now? The model, if you remember, this model is what corresponds with the between group numerator in ANOVA. This error is what corresponds with the denominator in ANOVA. So if it is multiple regression now, because you have many variables, all of them form the model. All from b0, the intercept, which is a constant, plus b1, s1, b2, s1, b3, as many as possible. Because this plus means that it can be, depending if it is 7 variables that are there, all of them form the model. Why this error? So all of them form the numerator, like what you have in ANOVA, and this error form the denominator. So for the model, the degree of freedom is equal to the number of predictors. So if you remember, the number of predictors mean for this simple regression, there's only 1 predictor. For simple regression, if it is multiple regression, you have more than 1 predictor. So like this one, x1, only 1 x1 is the predictor. If you remember, the number of parameter here is this b0 and this. So if you remove, there are 2, you remove 1 from it. This you remove, minus, it give you 1 degree of freedom. So there are 2 parameters here. 2 minus 1 give you 1. So we know that the constant is usually 1, 1, 1. So if you just say, either you say the number of parameter estimated there minus 1, knowing that the degree of freedom is something minus 1, or just say the number of predictor, because you know that whenever you remove the constant is usually 1, you remove it, just say the number of predictors. Like now, if you have 3 predictors here now, so the degree of freedom will be 3, because there will be, if there are 3 predictors, 1, 2, 3, then the parameter estimate will be 4, including this view. So if you remove 1 from that 4, it gives you 3, which is equal to the number of the predictors, degree of freedom for the model. Now, for the residual, degree of freedom is the number of observation sample size minus the number of coefficients in the regression model. You already told. So All you just need to do is that the total degree, the degree of freedom for residual would be the sample size minus, just remove the number of coefficients. For this simple regression, the number of coefficients is 2. This B0 and B1. For this one, if there are 3 predictors here, the number of coefficients will be 4. The degree of freedom for the residual will be the sample size minus that 4. So now, the total, okay, the total, let's look at it, the table, something like, is it table or not, picture? So K here is number of predictor, independent variable. I've already said number of, let's say, like for this simple regression, number of predictor is 1. For let's say this one that are 4 now, 4 predictor, only 1, let's say 3 predictor, let's forget it. Let's say there are 3 predictor. So the K will be 3. You already said it. So that is why when you look at the degree, look at this degree of freedom now. Under it, the regression, which is the model, the regression is the model, the degree of freedom is K, the number of predictor. Then the number of coefficients is the number of predictor variable plus 1, which I've already said, parameter estimate or the coefficient. So now you add the number of predictor from the constant, it give you the parameter estimate. So for the residual, which is the rest here, the degree of freedom will be N, the sample size minus K minus 1. I already said it. Because this K is number of the predictor. This other 1 you are putting here is the number of, that is the constant. So if K, there are 3 K now, so this one will be sample size minus 4. This one will be K3, this will be 1. The total degree of freedom, as I've said it, is addition of all the degree, the reg and the residual. So if you add this one together, it will end up giving you, it will remove K. If you K, say N minus K plus K plus K. K will cancel this K minus K. It will be N minus 1. The total degree of freedom will be the sample size. And that is this now. The total degree of freedom will be sample size minus 1. It's the same thing with, it gives you the same thing with the normal ANOVA. In fact, the people when we run our workshop on ANOVA regression, the same data set, we run it as ANOVA, run it as regression. So you get the same thing, exactly the same. And that is why when you run regression, let's see, an output separately on ANOVA, it's the same thing. It's just the, you will see that it's the same. It's just the what they call it, the labeling. Why the other one they call it model, this one we say call this one model, that's what we say between group and within group. Yeah, we call it model and residual. So now the last slide, which I want to show you the other time. Let me explain it further here. Now you will see when you run your ANOVA, your regression, you will see something sum of square, SS sum of square. That sum of square is not this, is the same thing as when I say, okay, deviation from the mean, square it and sum it together before you calculate the variance. That's sum of square. In trying to calculate the variance, all you need to do is to this sum of square divided by the degree of freedom, it gives you the variance. So this sum of square you are seeing divided by the degree of, it gives you the variance, mean square. Can you see now? SS total over the degree of freedom total, it gives you square mean, that variance. Here, SS model, which is the regression, divided by the degree of freedom regression, it will give you the sum of square, mean square, which is the variance model. This one, SS sum of square residual over the degree of freedom of the residual, it give you the mean square residual. It's as simple as that. So now, what I just tried to is just to see through more light on the nomenclature. The nomenclature we use numerator element of F statistic in ANOVA versus regression. Numerator, denominator. What we call between group sum of square, SSB in ANOVA is what we call sum of square model in regression. So what you call the denominator within group sum of square, SSW, that's it, within group sum of square in ANOVA is called sum of square residual. So if you go and listen to our lecture on regression and ANOVA, you understand this thing very well. I just brought it in because we are talking about the F distribution. The F stat is the distribution of the F statistic. So here, so I don't know if there's any. I think there should be a question. Any question? Did anybody chat any question? I didn't see any chat. So it's so simple. So any question? So no question. Okay, if there's no question, no problem. He said that is very simple. Everything is straightforward. Okay. Or everything is confusing. Yeah, I want to believe everything is not confusing, it's straightforward. Okay, thank you for the session. Okay, if that's the case, if there's, I want to off the switch of the recording so that yes, can help be called a ratio. Yes, it's a ratio. F ratio, they call it F ratio also. It's a ratio. When you divide two things of the same unit, variance over variance, it's a ratio. It's F ratio. Okay, thank you. Any other one?